Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everybody. It's a real pleasure to have here with us Stefan Stapp from the University of Koblenz-Landau in Germany. Stefan is professor for databases and information systems, and he's cited among the top 10 researchers at DAB and the Semantic Web conferences. And today he's going to talk about some work that we've been working on with Don Syme from Microsoft Research Cambridge on actually using some semantic technologies to help make sense of data. But more broadly, Stefan has been working also on using semantic technologies to support software modeling. And I won't talk about what we've been doing and what Stefan has been doing with his team because he's just going to talk about it. I'll just mention that we came back from POPL like a couple of days ago where we had a workshop on data-centric programming and where there was a lot of interest actually into these approaches of bringing more tooling to help developers make sense of data. So with that, Stefan, please.
Thank you very much for your kind introduction, Evelyn. So the work I talk about includes a couple of people from my team. It was initiated actually by Evelyn and Don to look at how can we bring some of the semantic web technologies, semantic web data structures into F#. And among the people from my team, there's Martin Leinberger. He's a PhD student in our team, and he's also there then to later on show you some demo, because I must frankly confess I'm a little bit too far away from the code base really to show this in a competent manner. Okay, so our point of departure is this quite famous picture from a linked open data cloud. For those who have not seen it, maybe who of you have seen it before? I guess many will have. No, not so many. Okay, so what does it symbolize? Each of these bubbles stands for a data source. And then some colleagues from Mannheim, Chris Beiser and his team, they have collected how these different data sources, each one of these bubbles has hundreds of thousands or millions of triples of facts, and how each of these data sources is connected to other data sources following the semantic web paradigm. Okay, many of them are connected to DBpedia, and DBpedia is the fact base derived from Wikipedia. Right? So stuff that drives also knowledge graph and other kind of approaches. And the interesting thing about this is that it's like the web, but not on a document base, but on a fact base. And what is also interesting is that this data has a lot of different data structures, a lot of different schemata. Well, and some of that has actually very little schema in just the facts. So it's very heterogeneous, and by now it also is actually more than 30 billion RDF triples. And even some famous database researchers, here's for example Gerhard Weikom in his Sigma blog says, this is actually a nice kind of environment to try your approaches if you deal with heterogeneous data. And if you think of big data, not only in terms of having massive amounts of a simple schema instantiation, but if you think in terms of having a lot of variety of data. So I will use this as a kind of motivation for my talk, though it's very clear when I talk about understanding new data sources that come in, it need not be this kind of linked data that semantic web people look at. It could also be just your relational data source that you encounter where you don't know the schema and that you have to deal with. So when we look at these different bubbles, each one representing an individual data source with millions of facts, you see that when you look at them in detail, you have very different domains. For example, here you have stuff about PubMed, for example, so from the medical domain, or drug bank, gene ontology, this kind of thing. Then here you have a kind of column which is about publications from the ICM or from the DBLP server, which provides you a bibliography, or from here's our partner, the Leibniz Institute for Social Sciences, with whom we collaborate very closely. They look at publishing metadata and all kinds of data about scientific literature in the social sciences. Here you have stuff about geographical information. Here you have stuff like New York Times is publishing a lot of linked data about the articles they have. It's just putting them on the web and making them accessible. BBC is doing the same kind of thing. So you have this media domain, which is very active. And then you have like these generic data bases, fact bases, like DBpedia, but also like Freebase, which is actually part of Google, or like Yago, which was done by Wycombe and his team. When I talk about a few more of the foundations of the semantic web, I have to explain to you the very simple foundation that we have there. What is this very simple foundation? We talk about data, and data for us is simply that you have some subject, and each object, or here this particular subject, is represented by a URI. A URI is nothing else than a globally unique identifier. So with this globally unique identifier, you can take this identifier and ask for, please give me more information about you. Okay? And such subjects are related via a specific predicate to an object. This object can be another URI. It could also be just like a string or an integer. And that's the very simple data model behind RDF. So extremely simplistic, much poorer than relational databases. But at the same time, like a common denominator for publishing data. And for this piece of data, you can describe a schema. And that schema has classes, and it can have class hierarchies. You will see a very trivial example from me on the next slide. And you can describe how different classes are connected by predicates. And the predicate has a certain domain constraint and a certain range constraint. RDF is very simple. You don't even have cardinalities. If you want to bring them in, you need to have a more sophisticated standard, which is called OWL for the web ontology language. Okay, here's a very simple example, a little bit trivial, but I think nice enough to tell you the story. So what is the example? Here, RDF resource is like the kind of top class that includes everything. And then you have a subclass like creature. All these URIs, they come with namespaces as you know them from XML. So you can really distinguish, let's say, a creature that I describe in my examples, or a creature as it would be described in some biology domain or in some other domain as you like. And we always abbreviate them here just to make it more readable. But you could mix them completely. You could take some URIs that are coming from the Microsoft domain with some biology domain with my examples. You could mix them all together in a giant global graph. And here for this class creature, you have several subclasses like dog or person, and you have attributes described like has name and has age. And we could continue here to describe what are the range constraints. For example, that the name would come as a string or that age would come as an integer. We have left it out of the picture here. And then here you see another example where between dog and person there is a relationship, the has owner relationship. So the domain is dog. A dog may have an owner, which is a person. And this is all the schema level. And here you also have the data level where Bob then, well, Hasso is a dog, having an owner, which is Bob, which is a person. Okay? So very simple example, nothing very fancy about that. When I talk about this example, please always keep in mind this may directly be an RDF data source, or maybe you take an established mapping of, let's say, a relational data source into this very simple kind of framework. So there is, for example, this standard here, R2RML, that was standardized like 1.5 years ago by W3C. This is the W3C recommendation. And in the meanwhile, there are very efficient mappers from this relational world to this kind of triple world. And when I mean with very efficient, some colleagues like Juan Sequeda from Texas, they have execution engines where it doesn't basically make a difference whether you then ask at this triple level or whether you ask at the original relational level. So you can really efficiently map between these different worlds. The interesting part here is that I will assume in the largest part of this talk that I have a nice schema description. As I told you for the linked Open Data Cloud, That's not always true. Some of the data do not have schema, but that's like the rest of my talk at the very end, where we'll talk a little bit about that, how we can deal with the situation when we don't have an explicit schema description. And also, to make it simple, I don't talk about different schema languages, I just talk about this schema language and this kind of data level. Okay, and that describes the agenda of my talk. I first want to talk about, given these assumptions, how we can bring these data sources into the F# language and Visual Studio. How can we find out what is in an unknown data source that's out there among these hundreds of data sources that are now out there in this linked open data cloud, or that you encounter just by integrating another part of your company and integrating another data source that you have not dealt with before. In the second part, I want to go a little bit into a very preliminary user evaluation. I say very preliminary because it has a couple of flaws that we are aware of, but I think it still shows a certain tendency of what the approach does well and what it doesn't do so well yet. And eventually, if I still have time, I don't know, let's see, I want to talk a little bit about our indexing approach, where we look at this huge cloud and we need to find a particular piece of information. We want to find something about creatures, about dogs or persons. And of course, this kind of information may be spread all over the place, not just in a single data source. And initially, we may not know where it is. And then we have to look at querying such that we find the corresponding data sources and then explore them and integrate them and program against them. Okay, so let's start with this first part where we encounter some unknown data source. Yeah, just pick your favorite one, and then you want to explore this data source and program against the data that's available there. So I think that's quite a not so uncommon scenario if you do some integration of different databases. And for the sake of making this a little bit better understandable, I don't go so much into the formal definitions that we have in a tech report, but rather just show it more by example application. Here the example application may be again taking this tiny toy example that I gave, that you may want to collect dog license fees and want to send email reminders to the dog owners. And we assume here that we have this nice kind of graph again that I've shown you before. And you now have to do a couple of tasks to solve this very simple, to do this very simple program. So the first task that you have to do as a programmer, so as indicated here in the title, is to really explore the schema and find out what is in this data source. Yeah? So you really assume you don't know how the data is described there, and you encounter that. And you want to find the types that represent the data you're interested in. So, of course, you see directly here on the slide that this may be person and dog, for example. But of course, in general, when you approach the data source, you just don't know whether it's person or human, whether it's dog or canine, or however the formulation might be. So you really need to look around. And classically, this first task you might do with a kind of a browser, or if you work in a semantic web, you might do a SPARQL query, and SPARQL is another W3C recommendation that's around for a couple of years now. Now there's like at least a second version of SPARQL around, and there are different kind of engines that support SPARQL and support the data format of RDF in the background. And you could ask questions like, give me all classes where we have a subject that is of type of particular class. So you find all the classes that are around that have instances by such a kind of a query. And you can do that. But of course, it's not so easy to formulate the queries to explore this kind of unknown data source. You easily get lost. And if you are in a situation that you say you start here because that's the top class for all the different classes, it's not so easy by asking these queries to navigate through, because every time you want to do a refinement, you have to completely change the query. So that would be like in a naive approach. You would still have to do it like this. And then when you have found out, okay, I'm interested really in the dog and the person RDF type, well, then of course to program against that, you somehow have to mirror these kind of types in your programming environment. So basically what you have to do, you take these kind of types and you provide code types. So the terminology always overlaps here. So I try to speak, when I talk about RDF, of RDF types, and when I talk about F#, for example, I try to speak of code types. Yeah. So because both are, of course, typing systems, but the one is in your data source and the other is in your programming environment. And you somehow need to establish these type systems both, and you need to map between them both. Right? So you somehow have to, after you've identified these as the types that you're interested in, you have to establish these code types in F#, for example. So you might say something like a creature is a certain class, and well, it has certain attributes like has name and has age. And we then can have subtypes like dog, which would be another code type in F#, or person, and they inherit all the attributes from creature. And in addition, they may have further attributes like the #hasOwner property, or maybe some text number for the dog or so. Okay, and that's the second task. So the programmer now has basically to write this down, which is actually much of a copying task because the properties are not really new. They are already given in the schema of your data source. And next, of course, what you have to do is you have to do data querying. So you want to query, say, I'm interested in all dog owners because I want to remind them to renew their license for their dogs. Okay, so what do you have to do? Well, once you have here persons and dogs, you are interested in persons that are owners of dogs. So you may ask a SPARQL query, a naive approach, and just find these owners by putting forward this kind of query. All well possible. Be aware that in general, if it's an unknown data source, you don't really know what these relations look like. What's their name? And here they even look nice and short, but in general, these are very long, unique identifiers in the semantic web, right? So, or you may have long package names if you encounter a data source, and not just such a toy example. Okay, you have to write this query. And once you have this query, of course, you have then to instantiate your objects from this data source and manipulate them and program against them. Okay, so you have to develop the functionality around your query. So typically in F# you would have to formulate a query string. This would be, for example, this kind of SPARQL query I've shown you on the previous slide. And then you would evaluate this, and then you could iterate over it to create persons and send email reminders to them according to the emails that are described. And that would be like the 4 steps that I would identify here. So first, exploring and understanding what's in that data source, then creating your types in your programming environment, the code types, then querying your data according to that, and developing the functionality around that. And for that, sort of like turning these data instances into code objects. All quite nice and well, but a little bit laborious. And the idea of LITEQ was to say, let's try to put these different tasks together and provide a kind of a framework that just makes it easier for a developer to handle these tasks with fewer different tools and fewer machinery and less boilerplate code than we have so far. Yeah? And of course, behind these kind of ideas, you may already recognize, if you think of LITEQ and of type providers, so you will see some of these ideas shining through here again, and we'll have later on a comparison with regard to these kind of approaches. Now, the core idea of supporting these different tasks is to have a kind of query language, which we call NPQL. NPQL really is the node path query language, and it allows you to traverse the graph, traverse this RDF graph that contains information about the schema and contains information about the data. So the nice thing about RDF is that it hardly distinguishes the two. So they are not really completely separate. All of them, the schema information as well as the data information, is encoded in triples, and you can ask for these triples using SPARQL. And NPQL is just like you could say, syntactic sugar to formulate your SPARQL queries in a way that makes it easier for the developer to go through these different tasks with the same kind of the syntax and not having completely different syntaxes all the time. For this language, we have then developed 3 different kinds of semantics, right? So you want to just go through this graph, that's the exploration part, but then you want to query for data, and for that, well, we have some typical extensional semantics, no big surprise here. Yeah, that's just what you would expect. And then we have also thought, well, we do not only want to have the extension that is all the data that follow a certain pattern, but we really also don't want to duplicate the types that we have in that system there. So what we then defined is an intentional semantics for basically the same kind of queries that gives you back these type descriptions. So you don't have to reinvent these type descriptions because you just query for them. And then you sort of like can put them together with the extensional semantics. I will show you in a minute how this works. And once you have that, you can actually not only use that for nicely writing your code, but you can even suggest to the developer what next to write. And that's what I call here auto-completion semantics. So when writing these kind of queries, you are supported all the time with particular suggestions of what could fill into your query language at a particular point in time. So let me again show these different types of semantics and tasks by examples. So the first thing would be to say you want to explore this graph. So you start, let's say, with RDF resource, and then you have an operator here for subtype navigation, and then you go to creature. So you change from this context to this context. You go from one node in the graph to another node in the graph. This can become a little bit more complicated. You can start also at a different point of view, a different node in the graph. So you would start here with dog, and then you navigate along a property. Not very surprisingly, navigating over /owner, you land at the person node. And now we can define what happens then if we define the extensional semantics for that. Well, assume we are, for example, here at the dog node. We have navigated there from the top class down to creature, down to dog. We have, by this means, selected dog as our current context for evaluation. We can walk through the /owner relationship by this dot operator. And, well, then we can just extensionally evaluate what this query means. So this query is, it looks almost like an XPath query, with a little bit different operators. Then you just say, I'm now interested in all the nodes that fulfill these conditions. And if you think in terms of, you have been here at this dog, and you have navigated by this /owner relationship to person, you use the extension to retrieve all persons who own dogs, because that's the context from which you came, and you end up here with Bob, because Bob, in this example, is the owner of Hasso. Okay, so we have seen, we explore this path, and then we say we're interested in what are the kind of objects that fit my description as I was walking along the graph. Now, it becomes interesting. I mean, yeah?
So when you said that there's not much distinction between data and schema, does that mean if my query had been instead like resource to creature and then ask, and then follow dot subclass, I would get all schema elements that are subclasses of creature? Or do you have to get down into the data before you can use
So the extensional semantics here always looks then for the instances. What you could easily do here is you could do meta modeling. Yeah, and in fact, actually RDF has some meta model approach. So this, for example, creature is a subclass of resource, but it's also an instance of the RDFS class. Yeah, so you could walk from resource to RDFS class and then say with an extensional query, give me the extension of RDFS class, and to the extension of RDFS class, creature would belong. Yeah, so RDFS has this meta modeling kind of thing. And thanks for asking a question I forgot to mention initially. Please interrupt me all the time when you're interested in a particular explanation. I think that's better. Yeah, so that's easily possible. And remember, see here again this kind of query for which where we look for the extension. We can do the same kind of query, so navigate to dog and then to the owner. So that's the same kind of query as before. And that basically means we are interested in some persons here, like Bob. But now if we ask for intention, that means we do not look for Bob, but we rather look for the intentional description of the people down here. Right? So this expression now does not any longer refer to the instances like Bob, who are owners of dogs, but because we look at the intention, it looks at how can we describe the type of these instances. Right? And obviously this type has all the attributes of person. So this means that by using the same kind of query expression, we first get the instances, and with the same kind of query, only the last operator is different, we get the schema description of these instances, which we may then use very nicely for creating our F# type description. Yeah, so we can now say in F#, using this kind of query, I want to describe, oops, sorry, it's just an old version. Here it should describe actually the person class being returned here, and I have not updated this properly. And then you would just appear what has been retrieved according to the intention. The thing being here is that once you have formulated this query, you can then build this into your environment and say, please give me the objects, and type them at the same time. And you can use the same kind of thing for the exploration. So here we have a query that says, I want to go from resource to creature, from here to here. And then it depends on what kind of operators you use. I only given a partial account here of the operators. But let's say if you look for subclass navigation, this expression here would not be a complete expression according to our query description, because it really looks here for another class description, or class term, I should rather say. But what we can do here now is that based on the context up to here and based on this kind of operator, we can suggest what would be appropriate next terms to fill into this place. So what we basically do here at this point is we define these auto-completion semantics and do suggestions. And we do suggestions depending on the operators. There are some operators that look then for instances. Martin will show you one of them in the demo. And then the instances we derive using the extensional semantics of this expression, plus some further information. Or we can look at types and properties, and we derive the properties or types that may be appropriate in such a situation. Here it would be the types, according to the intentional description of the preceding query expression. Okay? So here, obviously, when we look for a creature, we may then look at, well, what are the subclasses of that creature, and suggest both dog and person would be appropriate subclasses, and these are suggested because these are the direct subclasses to the programmer who writes his code to complete his query. These are just some of the features, just one feature to give you a little bit the flavor of what LITEQ is about. Is a little bit more complicated query, not a lot more complicated, but a tiny bit. And what it does here is to say, if we start at dog, we may be interested not just in all the dogs, because there may be dogs without owners, and we cannot then have some license fee for them if they don't have owners, but we can only have license fees if there are owners. And then we can restrict the set of these dogs to those dogs that have owners, right? And this would be a corresponding query for doing exactly that. If some of you are familiar with description logics, are some of you? Have you encountered description logics before? It's a subset of first order logics. And this is very much actually like a concept description in description logics, where you then can look at such expressions and ask for instances of such a complex concept, and where you can also do kind of query subsumption. And that's what we are aiming at here. And of course, in this context, the dogs that have owners, this would include has. So if there would be another dog without an owner, that would not be returned here. Yeah. It's a very restricted form of querying. It's not giving you the full SPARQL support, right? It's very much focused traversing the graph and restricting the number of nodes that you're encountering. So it's, would call it here left associative conjunctive query. You cannot build arbitrary queries by this way. In SPARQL, you have like full power for all kind of conjunctive queries and more. We don't have that here. But that's by design at this point in time, because we really wanted to support the developer in writing these kind of queries and in suggesting to him what would be appropriate schema information, properties, classes, or even then on the data level instances to complete his query and to work with that, right? So we didn't target a full query language like SQL, LITEQ, or SPARQL, so, but rather a subset of that. So we had now the exploration task. You have also seen how this would be supported with auto-completion. We have the type definition task using the intensional semantics. We have the query task being supported with the extensional semantics. And the fourth task that I mentioned before in a naive way was to create objects and manipulate them and make them persistent, right? So you want to get the objects from your data source. You want to work with them and then also give the results back to the data source. And of course, for that, you have to develop functionality around the query. And if we look at how we can do this here, this would just mean, okay, just first some boilerplate code, like including our LITEQ mechanism. Then you have to define the data source. In the future, we will think about how to go from one data source to another data source in the linked open data web. But right now, it's just like you have to indicate where exactly this one source is. And then you write here your query. So given this data source, write a query, for example, for creature, navigating down to dog, navigating to has-owner. So the operators look a little bit different than I've shown you in the slightly more formal part, but they do exactly the same. And so what you get here are these dog owners. And then you can just take these dog owners and iterate over them and, for example, send them the email reminder. So the nice thing here is you directly get here this extensional semantics, and in this assignment, you also assign the types to these dog owners. It's not just that you have some arbitrary data objects here. These data objects are typed with at least person, and also with the hierarchy above person, including the creature. So you can use here then, in this expression, also like the information from the creature class, which had the name attribute, for example, or the age attribute. We have a preliminary implementation of this approach supporting F#. So this is the website. It's really preliminary, so it's not really anything like productive code. It's good enough to look at the basic idea. And we know quite a couple of things we have to do to make it usable in a productive environment. That will still take us a couple of weeks. But it's good enough to take a look and see what's the principle behind. And I would now suggest that we switch over to Martin, who will show you some demo of the system as it is now. And so we'll switch over the screens and also hand over for explanation to you.
Yes. So what we will do, we will actually query the data store. Well, a very simple first query would be to query for all dogs, which looks like this. In this case, we actually start one step below RDF resource, because RDF resource is always there. So we start at creature, and basically the data source behind it is exactly the same as we've shown you before in the schema. So we go to creature, we do a subtype navigation, and choose dog, and get the extension, and then we can do something like print out the names of all dogs. Get his name? No. And if we run this, we hopefully get a list of all dogs that are in our data source. Right now, it's well, as Steffen mentioned before, we're just using RDF schema. That's why you will always get basically a list of possibilities back, like here, a sequence or list that just contains the string hasso or bello, because you can't really restrict the number of triples in the schema, so we have to assume that there are always more. Yeah, so like this, you could get all dogs. And then you could also go on a individual level. So you could say, show me all individuals of dogs. And luckily, there are only 2 ones in our data source. So let's choose bello. And we want to actually get an object so we can work with bello. And we can now also print out the text number of him.
This is very interesting that dogs have tax numbers.
So that's sort of a literal German translation. So I had to look it up actually, so that you would say license fee number or something like that. I don't know. It's a German example.
Differences.
Or false friend among the different words.
All right, so the text number of hasso is 1, 2, 3, 4. So we can now go ahead and change that.
And you see this get text number, that's supported because we know the type of bello. Right? That helps us here to show the right kind of properties. That's again typing information.
Have you thought about having some operators that would be less ugly than
Yes.
individuals?
Yes, we definitely thought about it. This was just a first intuition. You know, we wanted to, we were excited to get started. And this was
I'm not
Yeah,
criticizing.
but you're right,
the
yeah.
first thing
So
that came to mind.
One thing, I mean, the first idea was also to have the kind of operators that I showed you before on the slide, but the implementation reuses the type provider mechanism in F#. And there we have to misuse currently, when we use that, this kind of notation. So because the dot notation already means something in the type providers, we were not completely flexible in choosing the grammar. Would we choose the grammar arbitrarily, we would go for something closer to the version I had on the slides.
Actually, we're trying to look into DSLs in F# in the future and try to explore a bit in this direction. But we're also open to other suggestions, so if anybody has a good pointer, we're happy. Yeah, so we just changed the text number of bello, and this will be persisted in the store. So if we run it again, it will still be the new text number.
And in the background, basically all these queries or manipulations are translated to SPARQL queries and SPARQL updates. So basically, we don't care about what kind of store is run in the background as long as it's SPARQL compatible.
Could you show, if I didn't know where dog was in the hierarchy, do you have a way to
Well, you would.
search the data context for any?
Right now, in this implementation, you would need to go down the hierarchy. You're right now really forced to start at creature, which is a huge limitation right now in this implementation. The only good thing is that the autocompletion can, help you in finding your type.
But conceivably, all the individuals under creature, like Bello exists under creature, that individual is.
Yeah, you could also do that,
It
but
doesn't go upward. It doesn't go up the class hierarchy.
no.
I mean, we could do that. Actually, in our first draft, we had operators for that. Then we wanted to keep it simple first, get the version going. I mean, it's still a middle of the project. It's not like finished.
I hear you.
And,
I just think about when people get data, right? The first thing you want to do is like see it, right?
Yeah,
What's the first thing you do
absolutely.
when you get a SQL
Absolutely.
table? Select star,
Yeah,
stop 100 star.
Yeah.
So I think that exploratory nature is.
Yeah,
really-
okay.
is
And well, the next thing we will have to do there is you can do in SPARQL limits like you can do in SQL too, so you don't get like millions of
Yeah.
individuals because it doesn't make sense,
It's
right?
sort of well, the 100 I assume is a limit in your type provider parameter.
Yes, that's
So there's sort of this trade-off that you're running
Yeah.
up against, which is the type provider framework and the underlying data, which is huge.
yes. That's, I mean, in the end, it's always problematic if you go to or if you would query DBpedia and would try to use individuals, you would just get overwhelmed by the results.
And you have actually more than one way to arrive at dog because you can arrive there by going down the hierarchy, but you can also cross-navigate, right? Like you've seen that with person. We could navigate from creature to person. We can also go to dog and then say who are the owners. So we'd also arrive at person. So there are different possibilities to arrive at the same types because you really have a graph. That's also a major difference to the usual type provider approaches where you rather have a tree in your exploration. So the tree is basically going down, for example, a certain hierarchy, and then you may have some data at the leaves of that tree. That's a typical way the free-based type provider, for example, works. But here we have this graph, which also makes it a bit more complicated to sort of like arrange all the interaction with the auto-completion engine. Okay.
All right.
So we switch back to the slide deck. I have here a comparison with different kind of approaches. It also, I think, tells you a little bit about how we would compare the approach. First, LITEQ. Well, LITEQ is, of course, very good at querying for the data and then also manipulating the objects. You have to define your types yourself in order then to use them and to work them with these program expressions. And of course, well, you don't have the schema exploration part. But working with the objects and querying, you have here the full expressiveness. For LITEQ, we have here two columns. One column is sort of like what we plan to have in the end, and the other column is what we have now. That's, of course, not yet the full thing. So even here in the end, we will not have full SPARQL, for example. So it would not be as powerful in querying as SPARQL or not be as powerful as querying like LITEQ. But that's like this trade-off where we really want to support the user in writing queries and be able to type them automatically, right? If we don't require this automatic typing, we can come with more complex queries. If you don't want to do the autocompletion, or if you do autocompletion in a very different way, that's another thing we're discussing now, how to better support autocompletion for SPARQL, then we would not have this kind of restriction. Well, we only have a subset of the operators that we have in our concept yet. And if you look to something like the free-based type provider, you have some sort of data querying, but it's much, much, much more restricted than even what we have now in LITEQ. Okay, well, here you have two kind of type providers. Of course, it depends how the different type providers are implemented. So it's a little bit difficult to say the type provider mechanism is like this because it really depends on the implementation. So we have indicated here two different type providers. one for XML and one for Freebase. So for example, the schema exploration that happens in Type Provider, which was also sort of like the motivation for us to do a kind of exploration. Well, clear.
Sorry, just trying to make sure we have apples to apples comparison here. When you say link, what exactly are you referring to? Just the query API level inside the runtime? Or are you referring to trying to have connectivity to an actual persistent store?
Not sure where you draw the line there. I mean, what you have here with link is you have certain possibilities for doing type inference because you don't have the query expressions as strings, but you really have them as code in your program. And you have, of course, all the possibilities for doing the querying in your program code directly.
When you say link, what is the data source?
Well, it depends, of course, what you query with, whether it's XML or whether it's relational.
Which is why I'm wondering what the column actually means. So for instance, if instead of link you put in entity framework, as a link provider, then you get number 2. And possibly you get number 1.
Okay, I was not aware of this, but we should look this up. Yeah. Thanks for that's called entity
framework.
Entity framework. Okay, I was not aware of that. Okay, now I was thinking of XML and the relational. Yeah. So for XML type providers, you have schema exploration, but for example, it's restricted here to trees. But the information also in Freebase is not restricted actually to trees. So that's why I even sort of indicated it's not like the full exploration of everything. Code type creation, including our current version, uses erased types. So for these erased types, the types are used at design time for doing the auto-completion, but then they're thrown away. And that has also some negative consequences in our current implementation. We don't have the full possibility to do a switch based on the type of an object at runtime. That's something we would like to have, right? So that's where we want to go here and have really the full types and the full hierarchy. But that's not part of the type hierarchy mechanism as it is now. Here I was not quite sure, so that's why I put the question mark, but we believe it's also erased types, but we did not do a full investigation. And for data querying, yeah. So here Freebase type provider basically ask then for the instances of a particular class. If you have the country class and you get all the instances of that, you would of course get all the countries, but not much more. And once we have the full types, not just the erased types, we can also do new object creations. Currently, we can't do that. So what we can do right now is really to take the objects, as Martin has shown you, and manipulate some attributes. But what we would also like to do is say, okay, here are these types like dogs from the RDF data source. Make me a new object and also make it persistent in the data source. And that's currently not possible. So we don't have that right now. But I think once we have the full types, that should be easy enough to implement. So that's a rough comparison to some of the related work. There's a lot to do now for LITEQ. So the current implementation, as I mentioned, is a prototype. I just mentioned this erased type problem. We need to do some optimizations with the code to have a full lazy evaluation, which we currently don't have. We also want to better analyze which types are really needed just at design time and which are really needed at runtime, so we can be sparsely add types to the programming framework. We, at least also now, we don't throw all the types into the DLL, but I think we can do some more optimizations there to make a more finer-grained distinction. What we also still need to do, and have not yet done because it's really just in the middle of the project, is to really look exactly precisely at our query language and its expressiveness and how it compares to other kind of approaches. And in particular, one thing that I think really interesting, which goes a little bit also beyond our scope, because we are mostly at home here in this data modeling world, looking at RDF We had quite some projects where we did modeling with UML class diagrams, meta modeling, and this kind of thing. And we can use description logics to explain a lot of that and the queries in that. What I think really interesting is then to look at the programming world and have type inference as you have in F# or in ML, and then see how these kind of types that are derived ad hoc, where you have dogs that have owners, these are kind of description logics like types that are then put into a lattice of different types in the data source description, how this mechanism would interact with type inference you have in your programming world, where you then derive new types. And I think that will probably be a non-trivial behavior, how these different lattices interact. And this could mean that you have new objects, for example, new objects that you have created, that you can place at a lower point in the hierarchy in the data source, or you may have more refined, for example, static analysis of your types in the programming world because you have all this type hierarchy that you take from the data source. So it's a little bit speculation here, but that's one of the research aims that we have there. So let me come to a little bit of the evaluation of LITEQ. We thought about how can we, and it's really a tentative evaluation. I would not sort of like want to say it's really like good enough to submit this to a software engineering conference, for example. But it's like indicating a little bit where the problems are and also like where the advantages are. So first we looked at how can we evaluate LITEQ at all, and then determined that the process as a whole is a little bit hard to evaluate for various reasons, because it's hard to see what would be the counterpart. And also we had practical problems. For example, we used, well, people from the institute and so on, but we didn't have so many test subjects that would know F# or even just like functional programming very well. So it would be quite difficult to come up with a fair evaluation. So we decided to rather compare only NPQL against SPARQL, and with the hypothesis being that NPQL with its auto-completion allows for effective query writing while being more efficient when compared against SPARQL. Right? And that, of course, means this is a very focused evaluation that even does not use some of the advantages of LITEQ, because it really goes only into the exploration part and the data querying part, and not, for example, in reusing the queries for doing programming then in task 4, where you code functionality against it. So we had 11 participants. Well, we actually afterwards eliminated one subject because the subject would not be able to handle SPARQL at all. He was able to handle NPQL, but not SPARQL. But we thought it then too unfair to sort of like include his times. So we still had 10 subjects remaining for analysis. Well, there were students, undergraduate students, PhD students, few postdocs. The setup was to have a pre-questionnaire about their knowledge, to have a classification, give them a little bit of training in RDF and SPARQL in case they needed that, and also NPQL, which of course was new for all of them. And then we had some tasks for them to solve, and a post-questionnaire about what they liked and what they disliked. So here's a little bit of insight into that evaluation routine. We looked at, well, what were the programming skills? Well, all were either classified themselves as intermediate programmers or better. Object orientation, 8 of them would say they are intermediate or better in that. Functional programming, only 4 would say they are intermediate or above. 4 would say they have no knowledge about functional programming. When we looked at functional programming, there are Lisp and Haskell, most often mentioned. F# was mentioned once here. And we looked at .NET. How would they know the framework and then be able to work in this environment? So we had 1 expert, 2 beginners, and 7 who had not encountered .NET yet. And then we looked at SPARQL. There were 3 individuals that said they would have intermediate knowledge or above for SPARQL. And we classified them in the next slides as SPARQL experts, and 7 had indicated less than intermediate, so we would classify them here as SPARQL novices. Then we had a training phase, about 20 minutes live presentation by Martin and another PhD student, Stefan Schegelmann, and indicated 2 SPARQL queries and let them work with the environment to write SPARQL queries. So give them a little bit ad hoc training, just 5 minutes, and also 5 minutes for NPQL queries and writing them in the Visual Studio environment. So they would basically know how to operate the corresponding tools. There were 9 different tasks to solve. Half of the tasks, so we split them up in 2 groups. And the one group would have half of the task in SPARQL and the other half of NPQL, and the other group was just reversed. So you just would not have a bias towards the one or the other kind of tasks. Half of the tasks were done using Visual Studio, the other half using SPARQL and the web interface. You had actually seen the web interface before on some of the slides. A very simple web interface. And the task types were really there to explore, well, how well can you navigate and explore the data? So it's corresponding to the programmer's task 1 of finding what the source is. The source was very small, just like 50 facts. So it was not a big task yet where you had thousands of schema elements and tens of thousands of facts or so.
So was that intentional? I mean, I guess was it because you couldn't find a source? Is because a big source was
no? Finding a big source is not a problem.
Oh, okay. Yeah. So why didn't you use a larger source?
This is a kind of preliminary trial, and there's also still the stuff that we have to do about optimization to deal with large number of facts.
The impact on the performance.
The impact, yeah. We will have that. I'm not concerned about that, but right now when we did that, it was not quite the case. And then retrieving and answering questions about the data, task 3. And we also included 2 tasks that were intentionally not solvable by NPQL. I mentioned to you that some of the tasks you just cannot do because you cannot count, for example. And so we wondered how what people would do or when they would back off and say, okay, I cannot do that. So that was by intention design. And well, we took the durations to task completion. Okay, so here is, I think, the interesting part. Again, don't take these numbers too seriously. It was still like a pre-trial. It was not like a full enough formalized. So the numbers lie a bit. But the tendency was really that the SPARQL novices really appreciated support by NPQL. The SPARQL experts did not benefit so much, even if you compare this number against that. There was a little bit slack because they were starting to talk about what were the advantages, disadvantages, and it was not a fully formalized trial yet. So that will be the next step. So it's rather really tentative results. We have to be a little bit careful about these numbers. But it shows you a little bit the effect that if people are really familiar with SPARQL, they would not gain quite as much. But the other ones, for them, it was way simpler to deal with it. And well, the unsolvable tasks then really, they gave people problems just to find out they couldn't solve it. For this, you need to understand what you can do and what you can't do. Here is an evaluation per task, so 9 different tasks. The gray ones were unsolvable. And then you see there's typically the average is a little bit better for NPQL overall. But there were also more novices here than SPARQL experts.
So how did you find completion of an unsolvable task?
It was really just taking the duration. It was so this will be the next trial. We have to just do a cutoff at 5 minutes or so.
I see.
Yeah, and eventually what they did, it was, for example, a task. It was a small fact base. So when we asked like how many dogs are there, they could just return all the dogs and count them by hand. That would be allowed. Yeah. But they could not directly say, count me the number of dogs, right? Which you can do in SPARQL. And of course, it also means that only with a small fact base, that's really possible, right? When you then have 1 million of dogs and then.
For enough time.
Yeah.
I was curious if they recognized that it was not solvable with the NPQL, basically.
Yeah, that would be a question.
Some of them did. Actually, some of them said, okay, I cannot count, so I'm going to write here not solvable. Others just took it as it is and counted without any comment and wrote the number down.
And the point, of course, is, I mean, you can always make the language more complex, but at some point you will lose this functionality of getting the types, yeah. And so that's a kind of trade-off point, which we still need to explore better and understand this better in a formal way. And then in the post-questionnaire, we asked this question: well, do you really want to explore data source in your development environment? 4 of them said yes. 3 actually said no. So maybe it's not for all of them. Maybe some would rather say, I don't care about that. Just and 3 didn't have a clear preference.
So as opposed to what? You know, I mean,
well, you can of course just have a browser. You can have a browser where you wander around, you get a nice graph, right. And there are browsers like that around. So. And then you just switch to your IDE and program it.
Write the code there,
yeah. I think part of that was also because like the IDE still was too slow, really. So I think when that becomes faster, I think that numbers will also change a bit. But still, it's still remarkable that some didn't like or didn't need it so much. NPQL is easier to use than SPARQL. Well, 7 of them would agree to that. But well, there's still one needs also better support when writing SPARQL queries. So basically, there's no good SPARQL query writing support right now. And we're looking into this question as well, because that would also help, of course. It's not so straightforward, because you have so many dimensions in which you can continue a query once you have written one line, that it's not obvious at all how to do that. If you have a large set of queries that people have already asked the query source, then of course you can do recommendations. But if you don't have that, it's not quite clear what to do. And then better response times. So that's one of the tasks we have to work on now. My conclusion is, tentative conclusion, that LITEQ is still in pre-alpha status. We see some advantages. And of course, once you handle things better, then some of that result will become stronger, I think. Okay, so we have, how much more time do we have? 20 minutes? Okay, so I can talk a little bit about my third part. We have now this framework for looking at an unknown data source, exploring it, querying against it. But the problem, of course, may be how to find this data source in the first place, right? And that's what the last part is about Schemex, constructing an index such that you can determine where to find certain information, and also then induce a schema if you only have facts. And that's happening quite often with the semi-structured data sources. So here would be a typical example. You're interested, for example, in some set of documents that appeared in some conference proceedings written by a computer scientist, and you would have a SPARQL query for that. So that's the SPARQL query. You're interested in some X of type document, of type in proceedings, where there's some creator that is a computer scientist. And you have the linked data cloud. And you want to find out where do you find such piece of information, right? If what we do is we compute an index and then can answer this question, which, for example, would say here in the linked data cloud, there is an ACM data source mirroring the bibliographic metadata of ACM digital library, and there's DBLPs, one of the other data sources. And there are some more, but here, these are 2 that you could ask. So what do you need to do then in order to query them? You need schema information. You need to know where data conforming to this or that schema would be around. And we need to look at 2 types of schema information. First, we need explicit schema information. An entity, for example, may be directly assigned to a class. So in the example, I assigned this variable to the class document and to the class in proceedings. That's an explicit assignment. But actually what you will see often, and there are a couple of papers out there now in the semantic web community that looked at implicit information. So quite often there's more schema information in how entities are related to each other than in the assignment to classes. But it's not always clear, so there's variance in there. Some data sources, it's really like the class information is dominating. Some data sources, it's really more information about the schema just by looking at the data items and how they are related to each other. And yeah, so the schema level index that we then built is for entities. And these entities are maybe related to particular classes, types. They may be related to other entities, other classes, and may be related to strings, integers, and other kind of built-in data types. And the idea is, of course, to say, well, we have certain structures, and we can map these structures to determine that in data source 1, 2, or whatever, we find entities that conform to this schema structure. So what do we do? Well, one is to say that we have type clusters. Type clusters are combinations of classes that appear together. So do we have, let's say, a president that also was an actor, right? So you would have a type cluster for this kind of entities. And you would then say for such a type cluster, where in your different data sources, your hundreds of data sources, you have entities that fall into 2 or 3 or 4 of these classes. Now here, we are interested in documents and proceedings, and we're interested in the type cluster, and we find that in DBLP and in ACM, we both have entities that fall into this type cluster. Then we have entities, and we say they're equivalent if they refer to the same attributes, to equivalent other entities. And what we do here is we compute one bisimulation. So if you have a little bit background in XML schema induction, people like Abiteboul and so computed data guides, and in order to come up with a schema description of XML documents that don't have an explicit schema description. And here what we do a likewise thing, we restrict it to one bisimulation. If you do arbitrary bisimulation, you may run into difficulties with regard to the complexity. But here we just look into for such a description, what are the kind of properties that appear together for the entities, and then we say, okay, these property combinations, they appear in certain data sources. For example, if you look at creator, then we would find that, for example, the BBC metadata, but also the DBLP metadata includes this creator property. And then we can combine this together with restrictions on the destination. So we say we have an equivalence class that's built by looking at a type cluster, like document and in proceedings, and a restriction according to one bisimulation, looking at the different properties, like creator. And that is restricted not to an arbitrary creator. For example, it could be restricted to a creator that is of type person. Other creator might be of type organization or something like that. And then we find something that belongs into this class in these different data sources, right? And so we have then here a schema description that's induced by a combination of looking at the different classes that entities have together with different properties that this entity have and their range types. And of course, the next step for us to do is that if we have data with little explicit schema information, we use this kind of schema induction in order to present it in the F# environment and say, here, look, that's the type that you can reuse. And then here you have the payload, the actual data sources out there on the web that you can query for this kind of data. So if you look at document and in proceedings, we have a type cluster. We can build an equivalence class from this type cluster and from the bisimulation that restricts creator to computer scientists. And then see that only in DBLP we have this kind of information, because the BBC does not have stuff that was created by computer scientists, I believe. Okay, and then when you then have a SPARQL query, you can look at exactly this kind of structural information in order to derive that you should rather ask DBLP than any of the other data sources to find entities of that kind. We can precisely compute how this looks like. we were then wondering about exploiting principles of locality. For one thing we did was to look at streams of data that come in, to say that when we parse the data, they're out there on the linked data web. We don't need to look at the full payload, but even if we just look at parts, we get rather good quality. So we do rather computation that's restricted to a piece of memory that we can handle easily. And we looked at empirically at how well this works, and we find that actually even with rather small cache sizes of just like 100K and so on, we end up with rather good values for precision and for recall. So we lose a little bit, but we don't lose too much even with rather small cache sizes. And that was actually also something we presented 2 years ago and at the Billion Triple Challenge. So the Semantic Web Conference always has these kind of challenges also for handling large data. And it was much appreciated because with the kind of hardware we could handle this very efficiently. Gave us a first place. So that concludes this part. We still need to explore further the schema induction part, the query federation based on these structures. One thing that we were intensively discussing also in the DAX seminar last summer was how to handle the querying of data in the linked data web. There are two main approaches right now. One is a very fine-grained one. You always ask a URI, give me your description. You ask the individual object. You can do that. It's easy to publish that. But if you want to do this for many objects, it just does not scale because you have too many messages. There's the other very expressive one where you open up your data source to arbitrary SPARQL queries. It's very expressive. You can ask select star and you get everything, or do all kind of interesting restrictions. But it's not a very stable solution. At least right now, the SPARQL endpoints are not very stable. And of course, it costs you a lot if people do arbitrary queries. So we were even discussing whether something like a restricted query language, whether it's NPQL or something in this direction, might be quite a nice trade-off between being too fine-grained, costing too many queries and too many network messages, and something which is too expressive like SPARQL and costs you too much. But it's still an ongoing discussion. And that brings me to my last slide. What is the future of these kind of approaches in general, or what we look at? Is to look at like searching for distributed data, would of course also include stuff like keyword indices and stuff we had in other systems with it, but not in what I described today. To understand this distributed data, and there are a few papers out there now from our group, from 2 or 3 other groups that look at what does it mean to look at statistics of these RDF data structure, to derive schemata, to understand what are the important properties. Most properties that are allowed according to the schema are not filled. So you have also zip-like distribution of how these properties are used. You can look at schema.org, stuff that's supported by Bing, supported by Google, and these properties are not like uniformly used over the different sites. Well, and then of course formulate intelligent queries. I mean, the one query indicated now for schematics was rather still a very fixed one where you know exactly what properties you're looking for. That will not always be the case. And program against the distributed data. And that's something which is rather ignored in the semantic web community up to now. But then maybe quite nice if you want to bring this community on board, because it's a pain really to write string-based queries that are very brittle and where you don't have type safety and all the things. And we hope that our kind of approach helps in this direction. So thank you for your attention.
There is any other question?
Do you have actual slides on what the tasks that used for the survey?
So we have some more information on the web page. I think, are the individual questions also there?
I'm not sure.
I'm not sure. We should put them there. That was the plan. Let me see. But definitely you can explore more on this web page. And if something is missing from there, just send me an email and we'll provide it to you in the one or the other way. Here. that was the web page.
All right. Thank you.
Thanks.